Hello everyone. So previously we had discussed on the lazy propagation in the segment tree algorithm, right? So today we'll be discussing on the topic persistent segment tree algorithm, right? So let's see what the definitions part states here. So yeah, let's see what the definition part say here. States here basically a persistent segment tree is a data structure that allows access to the previous versions of the segment tree even after the updates. So this part is very important. What it does, a persistent segment tree is a data structure. What it allows access to the previous versions of the segment tree even after the update. So this is where the persistent segment tree is different from this one normal segment tree, right? It's a versioned segment tree. It is a versioned segment tree. Again, persistent segment tree is a versioned segment tree, right? Where each update, whatever the update that we do, every update it creates a new version, right? It's a version segment tree where each update creates a new version without destroying or modifying the previous ones, right? So this is where it is very handy and very uh, helpful, right? So we have solved some problems on the persistent segment tree as well, right? So we have already completed solving the problems on the segment tree, the code forces one I'm speaking of. Basically we have solved around 15 problems, I believe. uh, 15 problems in the Java and 15 problems in the this one, what do we call, Node.js, using Node.js as well, right? So it's a version segment tree where each update creates a new version without destroying or modifying the previous ones, using the concept of immutability and path copying, using the concept of immutability and the path copying, right? So this is fine, I believe. Now let's move on with the explanation part. Let's get into the explanation part. First, a normal segment tree, what it allows efficient range queries. We know this one. We have just discussed the segment tree as well as the lazy propagation in the segment tree, right? So in the last 2 days, I'm speaking of a normal segment tree. What it does, it allows efficient range queries and updates, right? Like sum, min, max, right? So this is fine. However, when we update a normal segment tree, the older version is lost. We know this. Whenever we update the normal segment tree, the old version is lost, right? In the persistent version, what happens? Let's see. First point here is each update creates a new tree version by copying only the nodes, right? By copying only the nodes along the update path. What it does, each update, whatever the update that we do, each update, it creates a new tree version, right? So this is the version segment tree, right? Persistent segment tree itself is the version segment tree. It's also called as version segment tree, right? Name itself, the title itself indicates here, right? Version segment tree. Each update creates a new tree version by copying only the nodes along the update path, right? So this means big of logarithmic n extra memory per update, right? But big of one access to any past version, right? Yes, this means big of logarithmic n extra memory per update. This one we have to keep in mind. This is very important, right? But big of one access to any past version, right? So this is this persistent segment tree. This is perfect for the problems where we must query past states of an array efficiently, right? So this is helpful, or this is used only uh, where we must query past states of an array efficiently, right? So some of the use cases I have mentioned. This one I thought it is better to mention some of the use cases as well. See here. So this is helpful when version control of the array data, right? So this is helpful when version control of the array data. Also time travel queries, right? So this is helpful for the time travel queries as well. Also it is helpful for the offline range queries like sum in version v between left and right, right? So left and right. So let's see the same thing whatever we have discussed in the explanation, right? So let's see the same thing in the action in the form of code or the algo using the Python programming language, right? So first, let's do one thing. Let's go with a class node as usual. So I'll just go with class node here. So within this, let me go with the initialization or the construction part here. Constructor part, sorry. Construction. Oh, sorry. This is self. Along with the self, I need value that is assigned to the 0, left that is initialized to none, as well as right that is initialized to none. So this is fine, man. So the next part would be we have to store the segment sum. We have to go with the left child node as well as the right child node, right? So this one will be self dot val equals val. This is fine. Also self dot this one left. So we are going with the initialization part, right? So right, let me assign this one to, let me initialize this one to right. So we are storing the segment sum. We are going with the left child node as well as the right child node. This is fine. The next step would be, let's go with a build, right? So we have to build the segment tree, right? So let's go with a indentation has to be correct one. So this one has to be, we have to start from here. So this one def build. So let me go with array as well as left comma right. So this is fine. So within the build, if left equals right, then we'll just go with return node of, so this one array of left. We have already discussed this one twice. I don't have to tell this one, but still let me tell you, this is the leaf node that stores the single element, right? And now as this one segment tree is the is nothing but the binary tree, so let's calculate the mid. Let's move on with the next step. So this one is left plus right by 2. Right. Also, let me go with the left and right child for the build. So we will be having the left child and the right child, right? So this one left child. So we'll be recursively dealing this one. So I'll just go with the build, nothing but the function name that we have made use of, or the method name that we have made use of, array left, and also let me go with the mid here. This is fine for the right child. So let me go with right child here. So this one again recursively we have to deal with that. So I'll just go with array. So this one will be mid plus 1 along with the right. So this is fine. Finally, root equals. So this one will be node left child. This one left child value along with the right child value. So also we need left child and the right child. So left child along with the right child. This is fine. Finally, let's return root. This is fine. Yep, we are done with the build method. Simple, very simple one. Now let's move on with the update method. So I'll just go with def here. So this one is update. So let me go with method name update of the function update here. So this one will be previous. I need previous L, then with the left, right, index as well as the value as the parameters. So this is fine. Within the update, the first step, if you know, we have to create the leaf node with the updated value. When left is equivalent to the right value I'm speaking of, right? So this is fine. Return, we need to return node of this one, node of val basically. This is, we're just creating the leaf node with the updated value. Again, as it is binary tree, let's move on with the further steps. Calculate the mid plus right by 2. And next, let's move on with this one. So what if the index is less than or equal to mid? So then what we need to do, so let me go with a new left variable name here. So we have to recursively deal with it, right? So here this will be update of this one, previous dot left. This is fine. Ma L, this one will be mid index comma value, right? So this is fine. Let's go with a new right as well. So this one will be new right equals previous dot right. This is also fine. Else what we will do, else let me go with new left here. So this one will be previous dot left. So this is also fine. Let me go with the new right. So this one equals So this one will be, let me go with update here. Previous.write, comma, mid plus one, sorry, mid plus one. This is also fine, right? Index and value. Also, finally, what I'll do, let's return this one node of let's go with a new left. Yep, value of the new left that we got along with the right as well, right? So this one new right value along with the new left and the new right. So this one will be new left, comma, new right. We are done with the update method. Simple. Now we are left with only one method, nothing but the querying. So within the querying, we know we have to go with the conditions no overlap and as well as the total overlap, right? So these are the two conditions we mostly consider within the query method, right? So this one will be def. Let me make use of the query function of the method. So this one will be root left, right, query left and query right. So this is fine. Next step, what shall we do? If query left greater than right or query right lesser than L, so then what we will do? So when there is no overlap, we have to return 0, right? So this is fine. The next step, what if there is a total overlap, right? So then if QL query left, if it is less than or equal to left, and right, if it is less than or equal to QR, then what we need to do here, when there is total overlap, then we have to return value of the root, nothing but root dot val. Right, so then let's move on with the further steps, as segment tree is the binary tree. So we will be going with a calculating mid left plus right by 2. This is fine. Finally, let me go with the return. So this is, we have to deal this one recursively, right? So this one has to be root dot left. This is fine. Left mid query left query right plus, again let me go with a query root dot right. So this one will be mid plus one, right? So this one will be query left and query right. This is fine, man. This is it for the code. This is it for the persistent segment tree algo code, right? So this is it for the algorithm, basically, in simple terms, right? So whatever we discussed on the explanation, the same thing we have articulated in the form of code, or the same thing we have implemented in the form of code. Now, for the interactive purpose, let's go with the example usage, man, right? So let me consider array of elements here. So let me go with some random elements, 1, 2, 3, 4, easy ones, right? So n, let me go with length of this one array. This is fine. The next step would be we will be dealing with the different versions in the persistent segment tree, right? So without hindering the previous versions, right? So that's what we'll be doing. That is the reason we will be making use of the persistent segment tree, basically, right? So first, let's go with the version 0, meaning let's build the initial tree. So let me comment this one and write. So here version 0, right? So this one here, let me give something. Let me go with version 0 itself. This one, let me go with build here. Build of, sorry, this one will be array, comma 0, and the last index n minus 1. Right, so this is fine. Next, let's go with the version 1. Right, so I'll just go with here version 1. This is fine. So I'll just go with version 1 here. So let me go with a update here. Update of, let's update version 0. I'll just go with a version 0. Let me involve version 0 here. 0 as well as n minus 1, and let me go with 2 comma 10 here, right? So we are just in this one updating the index 2 basically from 3 to 10. From 3 to 10 again we are updating the index 2, value of the index 2 here 0 1 2. This is the index 2, right? So this one we are updating the value 3 by value 10. So that's what we are doing in the update in the version 1 by making use of the function or the method update. Simple. Next, let's move on with the version 2. So I'll just go with here. So let me go with version 2 here. So here, let's update the index 0 from 1 to 5. So I'll just go with the version 2 here. So this one, let me go with update. So let me involve version 1 here. Also 0 and minus 1 remains same. We are updating the index 0 from 1 to 5. We are updating the index 0 from 1 to 5. So this one we are updating the index 0 from 1 to basically to the value 5, right? So let me involve the value 5 here. Simple. Now we have to print for the interactiveness, right? We have to show the output basically. So let's query the different versions now. Let me make use of the print here. So this one, let me go with some 0, 3 here. This is fine. And version 0, this is fine. Yep. So this will be, let me go with a query. Yeah. Version 0. Yep. So this one will be 0, comma n minus 1. This is also fine. Finally, let me go with 0, 3. Right. So let me copy the same thing and paste this one twice. So again, let's go with 0, 3 itself. Now for the third one, let's change from 1 to 3 basically. So this one will be version 0, second one will be version 2, version 1, and the third one will be version 2. So this remains same 0, 3 and 0, 3. So as we are going with this one sum of 1, 3, let me change this one from 0 to 1 basically. Right. So now if I run the code, what is the output that I need to get here as sum of this one 0, 3 in the version 0. In the version 0. In the version 0, it's normal, right? The first one here. See this one. So when I sum this one, I have to get. So basically, just give me a second here. Yep. 1 second. And consider, yeah. So this one here, we have considered this one sum in the version 0, right? So this is basically 0, index 0 1 2 3. So this one will be 1 plus 2 plus 3 plus 4. What is 1 plus 2 plus 3 plus 4? 7 9 10, right? So this is for the version 0. Right, for the version 1, what we are doing here, again we have to consider sum from 0 to 3. In the print we have been given some 0 to 3 in the version 1. In the version 1, what we are doing, we are replacing this one. See here, this part I'm speaking of. We are replacing the index 2 value. Index 2 value here, this is 3, right? So this 3, the value 3, we are replacing this value 3 by value 10. So this has to be 1 plus 2 plus 10 plus 4, right? So this one output has to be, so here 1 plus 2 nothing but 3, 3 plus 10 13, 13 plus 4 equals 17. 17 is the output that we need to get here, right? So what we are doing for the version 2 here, so we are done with the version 0 and version 1. For the version 2, see here, we are updating this one. If I remember, yeah, we are updating the index 0, meaning this one here. Index 0, we have the value 1 here, this one, right? First one, index 1. So this one, index 0 value, we are updating this value 1 by this one, 5 basically. So this will be 5 plus 2 plus 3 plus 4, right? So just when we sum up this one, this will be 5 plus 2 7, 7 plus 3 10, 10 plus 4 nothing but 14, right? So we have got 10, 17 as well as the 14. So this is the output that we need to get here. Oh, did I miss anything here? So, oh yeah, sorry. This one, we have already updated the value from 3 to 10, right? So we have to consider 10, not the 3. So I got confused here, man. So this one, let me do one thing. Let me go with 5 plus 2 plus 10 plus 4. 5 plus 2 plus 10 plus 4. This would lead to 5 plus 2, 7. 7 plus 10. Just give me a second. So yeah, 5 plus 2 plus 10 plus 14. So this would lead to 5 plus 2, 7, 7 plus 10, nothing but 17. 17 plus 4, 21. But here, one more thing. So here, this is fine. We are going from 0 to 3, 0 to 3. Right? 0 to 3, 0 to 3 means from 0 to 3, entire sum we are considering. For the third one, we are considering from the index 1 to 3, meaning we have to consider only from this one, right? So here we have to consider only these three things basically, right? So these three things, we are going from the index 1 to 3. So this one would lead to 10 plus 4, nothing but the 14, plus 2 is nothing but 16. The output that we need to get here is 16. So this is 10, this is 17, and the final answer that we got here is 16. So this is the output that we need to get here as basically. Sum from 0 to 3 in the version 0, 10. Sum from 0 to 3 in the version 1, 17. Sum, the change here is from 1 to 3. We have to ignore index 0, right? So sum from 1 to 3 in the version 2, we need to get 16. So output that we need to get here is basically 10, 17, and 16, right? For this one for version 0, and this one for the version 1, and this one for the version 2. Right? I hope the persistent version, this one, persistent segment tree, this one algorithm is completely clear. Let me delete this one entirely. So we know now what is the output that we need to get. So before running the code, let me explain you this one entirely, whatever we have written. Very quickly, right? So this one class node, whatever we have considered, basically what it does, it defines the tree node containing the value, left and the right pointers, right? Containing value as well as the left and right pointers. This is what the node class does. So second, we are going with a build here. Build, what it does, it recursively builds the initial segment tree. It recursively builds the initial segment tree, line number this one 38 and 39, right? So that's what we are doing. So next, we are dealing with the update function or the method here. So this creates a new version of the tree without altering the old one. So this is nothing but the persistence. This is the reason we called this one. What do we call? We have given the title persistent segment tree basically. This creates a new version of the tree without altering the older version or the old one, right? The update method is very important here, right? So this creates a new version of the tree without altering the old one. So next, let's move on with the query method of the function. Here the query, this is nothing but the standard segment tree range sum query function, right? So version 0, version 1, version 2 I have considered here. This one from the line 67 to 74. So version 0 is nothing but the original version built from the array, this one, what do we call, array 1 2 3 4, and version 1 is nothing but this is created from the version 0. Basically this is created from the version 0, nothing but this value itself, right? Version 0 after changing the after changing index 2 to 10, basically index 2 value to 10. Array now behaves like 1 to 10 4 instead of 1 2 3 4. I have showed you this one, right? Just now I showed this one, right? So this is fine. Next, final one, version 2. This is created from the version 1. Now we have 1 to 10 4 in the version 1. So this is created from the version 1 after changing index 0 to 5. Array now behaves like 5 to 10 and 4, right? 5 to 10 and 4. So the output that we need to get here is 10, 17, and 16, right? So now we have idea on the algorithm completely. Let's run the code, man. So let me copy this one entirely. So let me give here Control J. So I'll just give Python followed by this one file name.py. Yeah. So see here, we are getting the output 10. So this one we are getting 10 and 9, somewhere something is wrong. So we have to get 16, 17 as well as the 16, right? First one, this is fine. This one, second one, and the third one. So this is getting 10 itself, right? So this is not getting updated. Something is wrong with the within the update method. Let's check. Just give me a second here. So what mistake I have done here is, so algorithm is correct itself. So basically for if within the print, I have given version 0 for all the three. This one has to be version 1 and this one has to be version 2. So this is considering this one version 0 itself for all the things. So that is the reason we are getting 10, 10 and 9. So this is basically correct, right? So for what I have given within the print, so we are getting 10, 10, 9, which was correct actually. But now we have changed from this one version 0 to version 1. The last line we have changed from version 0 to version 2. So version 0, 1, 2. Now we have to get the output 10, 17 and 16 as I had explained that one earlier, right? So let's check the same. I'll just give you a clear screen. Yep, now we are getting the output 10, 17 and 16, right? So this works absolutely correct. So again, let me tell you here, let me quickly tell you. So this version 2, this works accordingly with this array. Just give me a second here. 1 second. This array, where I have considered array? Yeah, this one. So here 1 plus 2 plus 3 plus 4 is nothing but 10. This one version 1 is nothing but we are changing the value of the index 2 from 3 to 10. So this becomes 1 plus 2 plus 10 plus 4 which is nothing but 17, right? So we are displaying 0 to 3 from the range 0 to 3 for the first and second one. For the third one we are displaying from this one 1 to 3 from the index 1 to index 3, right? So now we are changing the index from index value, this one index 0 value from 1 to 5. So this one will be 5 plus 2 plus 10 plus 4, right? So we are considering only these three, right? So this one from 1 to 3, the sum we are considering from 1 to 3 basically. So this will be 10 plus 4 and this one 10 plus 4, 14 and finally 16. So we are getting 10, 17 and 16, which is absolutely correct basically, right? So we are getting the desired output. This is it for the persistent segment tree, right? So this is simple, right? So now we have complete idea on the three algorithms. One is normal segment tree or the segment tree. Second one, lazy propagation in the segment tree. And also the final one is persistent segment tree algorithm, right? So we are done with the segment tree algorithms, but tomorrow what we'll do, let's discuss the Fenwick tree algorithm, right? So let's discuss the Fenwick tree algorithm tomorrow. So now we are done with the persistent tree algorithm. So let me summarize whatever we have learned so far, right? So just try to remember these 2 to 3 points, man, right? So just give me a second here. Persistent segment tree keeps the history of changes. We know this one, right? Each update creates the new version. Each update creates the newer version. Just remember this one, right? So this is fine. This is the first point. And this is memory efficient. Why it is memory efficient? Because it copies only because of logarithmic n nodes per update. It copies only because of logarithmic n nodes per update. Just remember this one, right? So this is fine. The third one is it is perfect for the problems that involves time travel queries or immutable data versions. This one I have mentioned this one within the this one use cases itself, right? So you can just go through this one as well, right? So this is very helpful or perfect for the problems involving time travel queries or the immutable data versions. So the core concept of persistent segment tree here is path copying basically. Only the path, this is from only the path to the changed leaf is rebuilt here within the persistent segment tree, right? So this is it for the persistent segment tree. These are some of the very important points that you need to remember when it comes to persistent segment tree, right? So this is it for the persistent segment tree algorithm. Next, as I've said, we'll be discussing on the topic Fenwick tree or the binary index tree, also known as BIT, right? So for now, this is it. Thanks for watching, guys.